Hello, AP Physics students. I'm going to explain the math behind the AP Review FRQ that we practiced in class this week. So if you'd like to know how you can prove mathematically what you needed to conclude in your paragraph length response, follow along with me. So here is the question. Hopefully you can see this shared on the screen now. We've got a robot that is shooting an object and landing on the target. It says a group of students prepare for a robotic competition and build a robot that can launch large spheres of mass capital M in the horizontal direction with a variable speed and from a variable vertical position and a fixed horizontal position x equals 0. The robot is calibrated by adjusting the speed at which the sphere is launched and the height of the robot's sphere launcher. Depending on where the spheres land on the ground, students earn points based on the accuracy of the robot. The robot is calibrated so that when the spheres are launched from a vertical position y equals h and speed v0, they consistently land on the ground on a target that is at a position x equals d. Positive directions for vector quantities are indicated in the figure, and you can see up on the right-hand corner, it shows up and right are positive. When the students arrive at the competition, it's determined that the height of the sphere launcher can no longer be adjusted due to a mechanical malfunction. Therefore, the spheres must be launched at a vertical position of y equals h over 2. However, the spheres may be launched at speeds of v0 or 2v0. And so the scenario here we see at the top, the target is 4 points if you can hit it. If you fall really short, you only get 1. If you fall a little short, you get 2. If you go a little bit long, you get 3. And then if you go much farther, 2 and 1. So you can see they're trying to get as close to the target as possible. So what you're trying to conclude is that if they lower the height, obviously it's falling for a shorter amount of time. And if it's falling for a shorter amount of time, at the same initial speed, it's not going to go as far horizontally because the horizontal distance is rate times time, since there's no acceleration horizontally. And so if the rate is the same as it was before, but it's falling for a shorter amount of time, it can't go as far. If you double the height, or sorry, not the height, if you double the velocity at that lower height, the question is, will it then hit the target, or will it still fall short, or will it go longer? And you can proportionally reason that it will go longer, but I want to show you how you can mathematically prove it. Now the question says, in a clear, coherent paragraph length response that may only contain diagrams, or sorry, that may also contain diagrams and or equations, describe the speed at which the sphere should be launched so that the students can earn maximum number of points in the competition. And so hopefully you've looked at the rubric and you've seen what needed to be included in that paragraph. But here is how you can mathematically support it. And I think the most logical approach is to just compare what would happen launched at the normal height as compared to launching at the lower height. So I'm just doing it in 2 different colors here. In both cases, we're going to use kinematics equations, and I'm using something I've seen illustrated by Greg Jacobs, who wrote the book 5 Steps to a 5. And he calls it the rule of ones. And if you've been watching videos on the AP Classroom website, you might have seen this as well. So he's saying we're going to input ones and zeros or any just numbers that we know, 1 for anything that's staying constant, and then the changed number for anything that's not. So here we could know at the normal height, its position vertically is 1. We're just calling that 1. We don't know it's 1 meter, 1 what, but we're just saying that's fixed at 1. The initial velocity is 0, so that does not factor in. Half is a constant. The acceleration is not changing. It's due to gravity, so that's 1. And we're figuring out if everything was just constant at the base values, what would the time be? So if we solve for t, we get the square root of 2, which is a 1.4. Now, if everything was truly an acceleration of 1 and a height of 1, that means 1.4 seconds, but it probably isn't 1 meter height, and it definitely isn't 1 meter per second squared acceleration. So this is just a ratio proportion value for us to compare to other values. If we come over here to the lower height and do the same process, but now say that the height is half the original. So now instead of using 1, I'm using half of that. The initial velocity is still 0, and the acceleration is still constant, so I keep it as a 1. Now when I solve for t, I get 1. So as we concluded just conceptually, it should, at a lower height, fall for less time. And we can see mathematically, proportionally, it is 1 as opposed to 1.4 at the original height. All right. Now, knowing that distance-wise there is no acceleration, it's just the distance equals rate times time. So if we go back to our original scenario where the time of fall would be 1.4, and if we keep the original velocity, we just call that 1, that means our target is a distance of 1.4. Again, this is not 1.4 meters. This just means proportionally, it is at a value 1.4. If we go to our less time, so when the robot is shooting from a lower height, we said that the time would only be 1 as opposed to 1.4. So we're putting 1 in for time. And if we keep the original velocity, because the problem said it can only be the original or double. If we keep the original velocity, then the distance is 1. So again, we're proving proportionally, if the target is at a distance of 1.4, this would fall at a distance of 1. So well short. And if we look at our picture, that would at most earn 2 points. All right, and it's more than half, so it'll definitely fall in the 2-point range. Then if we do the same thing for double the velocity, we still keep 1 for time because it's only going to fall for this value of 1 at half the height, but now we're doubling the velocity, so we put a 2 in for the velocity. And this shows us our distance will be at a value of 2. That doesn't necessarily mean double the original, it's just double this one. So if we compare it to what it would be at the original value, we can see originally it would fall at a distance of 1.4. That's where the target's at. If we shoot it at the original velocity, but half the height, it's going to fall short at 1, not 1.4. If we shoot it at the half the height, but double the velocity, it's going to land at 2, which is beyond this target. Okay, but that should still fall in this 3-point range. So that is how you can mathematically prove that the time is less at a lower height of launch, and that the initial velocity and double that initial velocity fall short or go too far compared to the base values, all with proportions and not actual numbers. So I hope that helps. If so, then that will help you be more fluid and more complete in your explanation as you write that coherent paragraph length response. All right, thanks for watching.